So please welcome Dr. John Bloom.
You're going to get a bit of a side view of me because when I click this, it doesn't necessarily happen up there. So I'll be doing this a lot. Sorry about that. Anyhow, the idea tonight is to look at some of the evidence from the world of astronomy and physics for why it might be reasonable to conclude that there's a designer out there. And in particular, we'll be looking at these fine-tuning arguments. I teach astronomy, and one of the field trips that we take is we go out to some dark sky situations and let kids look with, or students look through telescopes and so on, and look at something like the Andromeda Galaxy. And it's pretty impressive, the reaction that everyone universally has, just how incredible and awesome the dark sky is, which we never see from Los Angeles, normally anyhow. And things like the Andromeda Galaxy. And I try to tie that into the Christian creeds that start basically with this comment, I believe in God, the Father Almighty, the creator of heaven and earth. And how large we can see the heavens now are all part of the creation of God. And how big God must be then to have created these things that we can marvel at. If God can create the universe, then it's no problem for him to come along and create us. We're just easy if you can create galaxies and things like that. But yet from the secular world, the argument is well, there's other explanations out there for how we could have gotten here. I mean, law and chance and so on. We could be here just because we're the lucky throw of dice. And the Andromeda Galaxy is here and we're here too. So that's sort of the question this evening is this. What are the odds that there could be complex life in the universe? Or anything anywhere else in the universe is the way astrophysicists often tend to ask that. And if the chances are really low, 1 in 10 or something like that, okay, we're here because we were that 1 in 10 that actually happened. But if we're here and we look at the odds that something like the Earth and the universe could have happened the way they are for us, those odds are 1 in a billion or something like that, well, maybe it is something like a miracle that we're here. And this idea has something behind it in the world of astrophysics. It's known as the anthropic principle. And some people call this anthropic coincidences. And the picture is basically this. And the question is basically this. We look around at the universe and say, okay, what are the factors that are necessary for complex life to be possible? Not necessarily life that has 10 fingers and 10 toes and looks like us or something like that, but complex life that can develop a technology, maybe send out radio signals that we could pick up or something like that is often how the astrobiologists would define that. And this is a type of design argument, that the universe is designed for us to be here. And a lot of people think that, well, Darwin sort of did away with those because he particularly argued that, complex living things are just like the gears of a clock, and, if one generation didn't quite get it right, then through mutation and natural selection, adaptation, the next generation would be better and better and eventually look designed, but it didn't originally start out looking as good as it does now. So in biology, design arguments have been attacked quite well because of Darwin's adaptation ideas. But in the area of astronomy, it has some problems to dismiss it as adaptation because you've only got one chance to get the universe right if you're making universes. And you can't, this planet Earth isn't giving birth to other planet Earths. So you're really throwing dice when you're talking about what are the odds on finding other planets or making universes with our features. So it really does boil down to a chance argument because adaptation over time isn't really a possible thing in the world of astronomy that we are familiar with. So what exactly are we doing with this anthropic principle? Again, we're looking for factors that make it possible for us to be here. or any form of complex life imaginably like us to be here. And the features that we'll look at this evening are, one, the precise structure that our universe has. And secondly, we'll look a bit at the delicate balance of physical forces that we find in the universe around us as well. And my main focus here is on secular arguments, ones that non-Christians make and pause over. And in the final sentence in the physics text that I use, when he starts talking about cosmology, this is the end of the book, where he says, it might even seem that the universe is exquisitely tuned, almost as if to accommodate us. Kind of a provocative ending to the book. And to me, what got me most interested in these kind of arguments was about 10 years ago or so. I was at a conference where Michael Shermer, who was mentioned earlier here, was speaking. He was speaking against intelligent design, but he said, as part of his introduction, you Christians out there, your ID stuff is, it's really crazy. But let me tell you, your design arguments, these anthropic principle arguments are the best thing you guys have. So if this stuff keeps Michael Shermer awake at night, who's a rather famous atheist, then it's like, well, maybe Christians should be using these a little bit more, would be my point. So let's take a look at this, and a lot of these hinge on this question: how exactly did the universe come to be? And the main theory that you hear about this from the secular world is known as the Big Bang theory. And I have to qualify that this is not some stupid TV show, okay, with a bunch of idiots trying to be physicists or something like that. No, this is a different model. This is the idea that, look, the whole universe, everything out there, came from a single enormous burst of energy, and as that energy expanded and cooled, some of that energy turned into the matter, the stuff that formed the galaxies, the stars, and us. It's very profound overall theory. And this is often a picture that's given for it, that the universe began with a quantum fluctuation, expanded dramatically, and over the course of that, matter formed that eventually became stars and galaxies and us, and so on. And of course, I would look at this and add a few things to it. I don't think quantum fluctuations were spontaneous and that started the universe. I think there was a little something behind it that got the universe going. And even once it formed, it didn't run on its own for 13.7 billion years. I think it really had to be guided and shaped and directed along the way. I want to show you some of that guiding, directing, and shaping. So, what's so anthropic about this Big Bang theory? First point is, it's not a bang at all. In fact, it was first used as a sarcastic term by Fred Hoyle. Basically, it's really stupid to think that the whole universe began with something like a Big Bang. He did not like the theory because it implied there was a beginning to the universe. But in the 1970s, people started to do some computer modeling about how the universe would have started from something smaller than the head of a pin and expanded to give us all the material that we see today. And people discovered very quickly, good grief, this had to be incredibly finely tuned, that it had to expand to within 1 part in 10 to the 55th at exactly the right rate, or else it would have fallen apart. 1 part in 10 to the 55th slower, it would have expanded and then collapsed back on itself in a big crunch. Or 1 part in 10 to the 55th faster, it would have dissipated so rapidly that it would not have formed any galaxies or stars. So it's this incredibly sharp razor edge that the universe had to expand, or else we wouldn't be here. Nothing would be here that would have any substance really to it. And thus the Big Bang had to be this beautifully shaped, incredibly carefully crafted expansion of that energy. Absolutely symmetric in all dimensions, absolutely controlled as it expanded so that anything like what we see would be here. So the picture, and looking out at all the galaxies and so on today, is it's not really a Big Bang. It should really be called something like the giant jewel. Okay, it's that incredibly, in fact, even joules are rough and coarse compared to the precision that the early universe had to unfold to give it the structures that we see today. This was the 1970s when this was uncovered, and when it was first done, this is where the term anthropic principle was first coined by Brandon Carter. And a lot of people just kind of shrugged it off as like, well, that's kind of interesting. But they kept finding other factors as they went along. And this is one of the other ones. You started to look at, okay, there's an awful lot of stars out there, but there's sure a lot of space in between all those stars as well. In fact, the stars are just kind of a little bit of dust in this huge, huge ocean of space. And people started to calculate about the, what we call the density in the universe. How much mass, stars, and stuff like that is there compared to the volume that's in it. And started to think about where that mass came from. Where did all that hydrogen and helium and the other stuff come from? Well, the picture is that it all started out as energy. As the universe expanded and cooled, some of that energy turned into mass, following Einstein's equation that you've all seen, the t-shirts, E equals mc squared. Turning energy into mass is what happened in the early universe. We use the equation in the other direction, m into e, to when we make bombs and things like that. But God did it the other way. He turned energy into mass. But when it formed mass, it forms pairs. It forms matter and antimatter. The equation for our interest should look something like this. Whenever energy turns into mass, you get a pair of particles produced. The plus one is us, regular matter, and the other stuff is antimatter that you've heard of on Star Trek and things like that. Well, what would normally happen is the matter and antimatter get produced and coexist for a few moments, but then when antimatter meets matter, they annihilate and turn back into energy again. So there should not be any mass in the universe at all. That's what happens when we try to do this in the lab. But there's something weird that goes on. About 1 time in 10 billion, when the pair production looks like it's going to happen, energy turns into matter and antimatter, the antimatter doesn't show up. You only get matter. 1 time in 10 billion. Well, that 1 time in 10 billion turns out to be just right, because if it was 2 times in 10 billion, there'd be way too much mass in the universe. And if it was half a time in 10 billion, there would not be enough mass for it to all wad together and form stars and galaxies. So here's another one of those, oh my stars, it just happens to be 1 in 10 billion as opposed to 1 in something else. The universe has just exactly the right amount of mass density, and it's kind of weird because it is weird that there's a huge amount of space for very little matter. But once again, that density turns out to be just right to give us the right balance in the universe so that somewhere in it there can be planets with maybe some intelligent stuff on it. Just the right density. To step back and not look at galaxies, but to look at whole clusters of galaxies, all those blue dots are galaxies close to us. The redder ones are farther away. If you can think in 3 dimensions, you can kind of see this as a foamy bubble structure in the broader universe. So there's lots and lots of space out there with this sprinkling of bubbles of galaxies. It's the structure that we see. But lots and lots of space, very, very little matter. And it needs to be that way for something like Earth to exist. It's stunning. This is the Earth ironed flat with temperature shown. The Sahara Desert's really hot and the Arctic is really cold. What I want to show you is what people were expecting a temperature map of the sky to look like. So center of the Milky Way galaxy in the center, iron the sky flat, and look at it. And this is what people were expecting is it really should be 0 degrees everywhere you look. And what they discovered, quite by accident, back in the 60s, was that it's not really 0 Kelvin, okay, not 0 centigrade, okay, 0 Kelvin. It's actually about 2.7 Kelvin. So it's not freezing, it's just freezing out there, is the idea. But that was weird. So no. If the universe has always been here, it's always been about the shape that it's in, there shouldn't be this background temperature to the universe. Where did that come from? And that's understood today as being this background leftover energy from the initial Big Bang. This was one of the major proofs for that Big Bang model. And over the years, we've gotten better and better pictures of what that background energy, the stuff that didn't turn into mass, looks like. And the first was, ooh, it's there. And then in the 80s, the Kobe satellite was like, ooh, it's got some speckles in it. The WMAP project here about 10 years ago was able to map it. And we see this very interesting speckle pattern that George Smoot called the fingerprints of the maker. Okay, so remember I had God's finger starting it? That's his fingerprints. Okay, that's little imperfections, tiny imperfections that show up as microscopic changes in temperature. You probably can't read the lower scale there, but it's only a few 10,000ths of a degree warmer in one region than another in the early universe. But it's that speckle pattern that gives that early energy and that early matter a structure to grow into. And that's the structure that is the foamy pattern that we see in the broader universe today. The red spots, the hot spots there, that's where there's a little bit less matter, so it turns into the bubbles. The bluish spots are where there's a little bit more matter. That's where it's going to clump into galaxies. So you see the early structure of the universe in that microwave background radiation that's there. So what? Well, that's kind of interesting. I mean, if those speckles were a little bit bigger than they are, if the temperature variation between the hottest and the coldest ones was a little bit bigger than it was, then we wouldn't be here. That's another feature imposed on the early universe that gives rise to the right size structures, the stars and galaxies that we see today. If there wasn't enough of a speckle pattern there, then there would not have been enough mass distribution. It would have just dispersed itself as hydrogen. If there had been too big a temperature variation or too big a speckles there, well, then you'd end up with the black hole universe. So the universe that we see today, with the galaxies and stars in it, comes from that initial imprint in the universe that's just right to form stars and galaxies. If that had been messed up a little bit, we wouldn't be calling it the Big Bang, we'd be calling it the Big Gas, or something like that. It would just be smoke out there, hydrogen drifting around, and nothing interesting would have happened. Or it would have been the fast flush. You know, a bunch of black holes would have formed, and boom, there goes all the matter, and it's all gone. So there's features here in the structure in the early universe that astrophysicists are finding that is just stunning. And this is coming from a secular model from people who are kind of sometimes gritting their teeth. It's like, this really does look a bit fine-tuned. To think about the balance here, good question to ask. You know, just how delicate does it have to be? I talked about 1 part in 10 to the 55th, 1 part in 1,000 or something like that. Just how delicate does it have to be? One good analogy that I came across for this is, okay, you look back at the early universe and you add or subtract 1 dime's mass in the whole universe back in its early stages. What would that do? That would mess up the way the universe unfolds to the point that you would not get the structure that we see. You'd end up again with that either vast clouds of hydrogen that are too dispersed to do anything interesting, or you end up with nothing. 1 dime's of mass in the whole universe. That's called fine-tuning at a crazy, crazy level, right? We're not talking 1 chance in 10 if you're talking one dime in the whole universe. Other features that are fun. The universe just turns out to be electrically neutral. You all know what electricity is. You've petted Fluffy and zapped yourself or stuck your finger in an outlet or something like that. You've encountered electricity, but at the level that physicists worry about it, it's like, okay, there's protons that carry the positive charge. Those are always in the nucleus. And if you were to look inside one of these, we discovered things called quarks that actually make up the proton. So if you could peel the surface of a proton back and look inside, you discover it has 3 particles in it. We can't separate them because the energies, they're so tightly bound we can't pull them apart. But nevertheless, there's 3 particles in there, and what's weird is that they have fractional charge. This really spooked people. It's like, wait, there's +1 for the proton, but that's made up of 2 things that are 2/3, plus 2/3, and 1 thing that's a minus 1/3. Do this on your calculator, right? 2/3 plus 2/3 minus 1/3 gives you 0.999999. It's like, wait, how does that end up being exactly +1 in contrast to the electron that's the negative charge in the universe? That's exactly -1, and it's a single particle. It's not made up of 3 things. It's a single particle. So just mathematically, you're like, okay, 3 particles get together and make a +1. That's exactly negated by a completely different kind of particle that's the -1. Now, why are they so perfect that they exactly cancel each other? As best we know, they exactly cancel each other. And what would the universe be like if they did not exactly cancel each other? Well, if they did not, you'd never hear about gravity. Gravity is so small compared to electrical attractions and repulsions. 1 part in 10 to the 37 smaller than electrical forces. We'd never be talking about gravity, and it's gravity that makes planets and galaxies and solar systems and so on work. Oh, and then there's something else. Not only are they numerically exactly equal, even though they're coming from different sets of particles, but the quarks were made at a different time in the life of the universe than the electrons were made. So here you've got all the stuff that's going to end up being positive, made at one moment in the universe. Then a little bit later in the universe, all the minus stuff is made. And at the end of that period, when all the minus stuff is made, it's exactly electrically neutral. That's rather finely tuned. Oh, yet another one. Okay. Well, let's look at how those protons get together and make atoms. Hydrogen is just a bare proton. But if you want to make helium or anything other than hydrogen in the universe, you have to start looking at how neutrons and protons get along with each other and make the nucleus of the heavier elements. Well, for them to stick together, you need something called the strong force. And it's very provocatively named because it's the strongest physical force in the universe that we're aware of. Okay, but it's like Velcro. It enables the protons to kind of stick with each other and allows especially protons and neutrons to really stick with each other when they're close enough to touch. If they're not touching, it doesn't show up at all. Well, it's that force, that attractive strong force, that overcomes the electrical repulsion between the protons. If it wasn't for the strong force, no 2 protons would ever stick together. But this overcomes the electrical repulsion and gives us what? The possibility of nuclei for electrons to hang around that are bigger than hydrogen. Well, just how fine-tuned is this thing? Well, if it was 5% weaker, we'd only have a universe with hydrogen in it. The strong force was 2% stronger, oh my stars. Then we'd have a universe full of mega atoms, and once more we'd be on our way towards a black hole universe. Let me give you a picture of what this means. Periodic table. Hopefully this is on the wall of every classroom at Fresno Pacific here. I mean, after all, this is truth for chemists, right? So the way the strong force and the electrical force balance out, it's right at bismuth, element 83. If you try to put more than 83 protons into a nucleus, it doesn't work. How long it doesn't work depends, on the stability of the nucleus, but everything's radioactive above bismuth. Everything below bismuth is stable except for technetium, just so that there's an exception for nuclear physicists to study. But if you tweak the strong force relative to the electrical force a little bit, you start losing the commodities market. Gold just disappeared, platinum just disappeared. It's now radioactive if you find it around at all. And if you carry this too far, that's the periodic table. Hydrogen. You really can't make complex, intelligent life from hydrogen. You can't even make stars from only hydrogen. Hydrogen has to do something, and it won't if the strong force isn't strong enough. So there's a limit on the universe. Let's make the strong force a little stronger. Then, now all these radioactive things start becoming stable, and you end up with a universe where the periodic table as we know it is a little blip off on the side, and there's tons of heavy elements around it. Who knows what they would do chemically? And theorists go, yeah, you'd end up with a universe that would be basically something like this, but a heavy matter universe would very, very quickly feed itself into black holes and not be around long enough to do anything interesting. So it's features like this that people look at, thinking secular models and stumbling across these incredibly fine tuning situations about the structure of our universe, just to have the basic chemistry, just to have basic stars, just to have basic galaxies here. And regarding the Earth, because there's been books written on the fine-tuning of the Earth, to mention one of them, Richards and Gonzalez's book, The Privileged Planet, they go through all the odds for just the Earth and end up with astronomical odds for the right kind of atmosphere, the right sort of gravity, the right amount of water, and various features associated with the Earth that I don't have time to cover. But it really is a situation. We're looking at a universe, looking at an Earth, where the odds of this having happened just by laws and physics and chance, it really does look like it's designed. And yet a lot of people will tend to go, well, we're here, so I guess it happened at least once. But I would point out that kind of misses the point, because the fact that we're here doesn't really address how we got here. Did we get here by chance? Well, that's the kinds of things we've been looking at. Or is there something else behind it? Is the reason why we're here. Unfortunately, science is kind of trapped in naturalistic only explanations. And so a lot of people will dismiss this and say, well, the only scientific answer that someone can give must be some naturalistic one. And I guess that is, that we're just the lucky throw of dice, because that's the only viable naturalistic answer. But I would say, wait a second, maybe there's something, maybe this data is showing us that naturalism is actually the wrong position to be taking, at least for features of our universe like this. And there's atheists who comment on this as well. Fred Hoyle, who's no longer with us, but nevertheless was a rather famous physicist in his day, made this comment. Common sense interpretation of the facts suggests that a super intellect has monkeyed with physics as well as with biology and chemistry, so that there are no blind forces worth speaking about in nature. So if secular thinking physicists, astrophysicists, and so on make comments like this, it's like, okay, why not consider God as a possible explanation for why we're here? And what I find interesting with this is that people keep finding more and more features like this in the structure of our universe. The first one was, that expansion rate. So there's a dial that you've got to get right to make our universe. And then, that mass density. Wow, that one's got to be just right in terms of how the matter and antimatter work out. So we've kept finding more and more dials that have to be adjusted just right to make the universe suitable for life over time. The first one you could shrug off. The second one was interesting. The third one was kind of interesting. But now we're at a point where physicists will say that the universe looks something like this. there's 30 or 40 dials. Oh, some have to be really precise. The range on other ones is a lot bigger. But we're really looking at a control room that looks like it was set just right for anything imaginably like complex life in the universe to be here. So what do people do? Well, the recourse to this is this. Since the odds are so small for our universe to be here, that proves that there must be lots of dice being thrown out there, and there have to be billions and billions of other universes that have to exist in order for ours not to be weird. If you throw the dice enough times, you'll get anything. And I guess we're the lucky one. It's like, well, there's a couple of problems with that. One is, this is called science fiction, I think, because something that you can't see, but mathematics might allow you to justify, classically has not been called science. It's been called a fertile imagination or something like that. But if you can't prove that it really exists, if you can't physically measure them or physically detect them, and kind of by definition you couldn't, because our universe is defined as everything that we can see and detect. So the fact that you posit other universes to avoid ours being so finely tuned and unique seems like a bit of a leap of faith, unfortunately. But there's a worse response than that, and this is where Bill Craig and philosophers have come in and said, wait a second, if you're going to ask, what's the most likely universe? If you're just going to throw dice, the most likely universe that you'll get is this. It's a lot easier to make a brain in a vat of nutrients that imagines all the experiences that you're having. The odds on the dice coming up that you're just an illusion, or well, that there's a brain here that's imagining the universe, is far, far more likely than, okay, I need to get Descartes in there, is far, far more likely to have that than a universe that has the extent in space and the balance of equations and the balance of properties in its material for us to be here. It's far more likely that this universe creating multiverse is making Boltzmann brains rather than us here. Or maybe I'm here just imagining that you're there because I'm a Boltzmann brain in a vat. So the philosophers have really, I think, kind of killed it because they've said, if the multiverse is true, then it's far more likely that you're just hallucinating your existence than that the universe really exists, than that it really exists. So if you're going to argue for the multiverse, I don't have to take you seriously because you're just a hallucination. Now, I would take you seriously because I don't think you're a hallucination, but that's what you have to respond to in the multiverse model. So what's happened here, I think, is fascinating. Naturalism, which says we have to think of just cause and effect and the laws of physics and chemistry and chance, has reached a dead end at being able to explain one of the most fundamental questions: how did we come to be here? And what's happened is because science has so embraced a naturalistic thinking, trying to push God off the square, and the earlier lecture was great. This divorce between God and science happened during the Enlightenment and the rationalist movement in the 1700s, that because of that movement, the rationalist movement to explain the universe in that way has ultimately failed. And we need to bring God or something like that back in to explain why the universe is here. It shows all the handwork and handiwork and craftsmanship of a designer as the best explanation for it. And just to give some secular comments on this, Robert Jastrow is an agnostic. He wrote a book about God and the Astronomers, how astronomers resisted the notion of the Big Bang Theory because it was too theological. Okay. And in the end of the book, he comments this: for the scientist who's lived by his faith in the power of reason, the story ends like a bad dream. He's scaled the mountains of ignorance. How did we get here? How did the universe get here? He's about to conquer the strongest peak, As he pulls himself over the final rock, he's greeted by a band of theologians that have been sitting there for centuries. Didn't you ever read Genesis? I mean, in the beginning, God created all this, you know. That seems to be the best explanation for it. And to return to the physics textbooks that I used, that final paragraph, nevertheless, questions of cosmology are deep ones that fascinate the human intellect. And one aspect that's especially intriguing is this. Calculations on the formation and evolution of the universe have been performed that deliberately vary the values, just slightly, of certain fundamental constants. The result? A universe in which life as we know it could not exist. He's secular, remember, okay. Such results have given rise to a philosophical idea called the anthropic principle, which says that if the universe was even a little different than it is, we could not be here. It might even seem that the universe is exquisitely tuned, almost as if to accommodate us. And what I would like to add to the text is this. The next chapter of the book starts with, and let me tell you a bit more about just how it was exquisitely tuned just for us to be here. The conclusion is to me pretty straightforward. And to give you more resources to follow up on this, John Lennox, if you want one book that's readable on this issue of science and Christianity, John Lennox, a British mathematician, has an excellent one, God's Undertaker is Science Buried Gods. Hugh Ross has an excellent book, Creator in the Cosmos. It looks at, I only gave you 4 or 5 arguments. He's got dozens. A more recent one that Hugh does, Why the Universe is the Way It Is, where he looks at a number of the features for the Earth and the universe that are really illustrative of that fine-tuning idea. But it's not just Christians and evangelicals who really lose sleep over these issues. Ward and Brownlee are two. Ward is an atheist, Brownlee is an agnostic. And this book, Rare Earth, is especially intriguing because what they say is, look, the conditions for intelligent life, for complex life with just the right habitat for technology and so on, is so delicate, is so finely tuned at the planet level, not just the universe level where I was mostly looking. But it's quite likely that we're the only intelligent life in the universe, simply because the average place in the universe is way too hazardous for life as we know it, or even can imagine it to be. So this, to me, is a powerful argument where science is actually pointing to there's somebody behind this. And to look at it in more detail, I will just refer you to, if I can give a little advertisement here, the MA in Science and Religion that we do at Biola spends a lot of time, has a couple of courses that work through this stuff in more detail. But just to wrap up, if I can take a couple extra minutes, here I wish we had the whole front as a screen. I don't know if there's any way to kill those immediate front lights, but I want to give you a look at the universe, the size of the universe, and a feel for that. Good, a little better contrast. This is a wide-angle shot of the night sky. See that little HUDF down there in the bottom? That's going to be our destination, the Hubble Ultra Deep Field photo. And I don't know if you can see the little thing there on the side beside that. The little round dot is, hi. Okay, that's the moon to scale here for the night sky. So what I want to look at is a little closer view of the night sky. There's the ultra deep field frame, and that's the moon to scale. Okay, so if you wanted to shoot the moon, if you wanted to shoot the entire sky, at the resolution that the ultra deep field did, it would take you 1 million years. Only 900,000 years. I shouldn't exaggerate. Okay. Because the Hubble stared for 11.3 days in space, detecting 1 photon per minute. It was its sensitivity level. I just cried over that. I mean, that instrumentation up there. If you've got billions of dollars to spend, I guess you can do things like that. But those speckles in the background are what's interesting. Okay, they thought they were looking at a pretty much empty region of space. Each of those little speckles in there is a galaxy. Okay? And there's about 10,000 galaxies in this tiny image. This image would be the size of a dime from 75 feet away. Or looking through an 8-foot-long soda straw, and you're seeing 10,000 galaxies. Yeah, okay. And the limit of vision with the Hubble is a little over 13 billion light years out. So we're actually able to see to the visible limit of the universe today, thanks to Hubble. I mean, we can literally see all of God's handiwork. It's like, it's awesome. It's awesome. So this is what I want to think about. Is like, okay, we look at a universe like this, and let me click back a little bit. I believe in God the Father Almighty, creator of heaven and earth. Okay, now we've got, finally, the ultimate image of what heaven looks like. I mean, the heavens look like, and the physical heavens look like. So this is sort of Romans 1, you know. Okay, now we can see what's been made. So what do you do with that? You can ask these sorts of questions. Obviously, the being who made this is really smart. And really powerful, too, because he blew these galaxies out like dust. I mean, this is totally incredible. But what other things could he do? What else? What's he like? You know, other than powerful and transcendent over this universe, that he can make it like that, which are the Romans 1 conclusions that Paul says. You know, anyone who looks around can deduce that there's a divine being who's transcendent who made this. But let's think about that for a little bit. A being that has the power to create billions of galaxies like dust would have no trouble whatsoever if he wanted to come to Earth and talk to us for a bit. He would have no trouble whatsoever healing the eyes of a blind man or something like that. As a matter of fact, that's just absolutely a logical thing that he would do, because he can't show them pictures of the Hubble Space Telescope because it hasn't been made yet. You know? So how do you get people's attention? Well, you come to Earth and you do things that are radical. That's a very logical thing for people to do. So this is where I find it tough for theologians. You know, theologians like, well, that God would actually do miracles would be really strange. Well, wait, if you're the creator of the universe and you can blow out galaxies like dust, then that's no big deal whatsoever. And then, some poor little girl died. Well, let's see, if you invented carbon and worked out the genetic code and designed all the proteins and everything else, you know, to get the Krebs cycle and a few little things in the metabolism going again, and some little girl, you know, that, you know, if we really, as Christians, appreciate what it means when we say that God's the creator, there's a huge number of things that make sense and are just absolutely logical for God to do if he wants to get our attention. If you got the power to make billions of galaxies and blow them out like dust and do all that fine-tuning along the way to make the universe have exactly that feature, and on some microscopic speck of dust, some ants decide to thumb their nose at you. Why not just have a convenient star go supernova, and over the course of 24 hours, you'll rotisserie that planet, and they'll all be gas, and you go create life someplace else. I mean, why bother forgiving something that you've made if it does rebel against you? That you don't deduce from looking at the universe. And that's the thing that is absolutely incredible, I think, about the God that the scriptures tell us about. Why would he do that? He didn't do that with angels. Why would he do that with us? I don't know. But then you go, wait a second, if he's going to decide to forgive those ants on that speck of dust, and he's the God who balanced electrical charge absolutely perfectly, who made it expand at just the right rate and set up all laws in physics in just a perfect balance, then maybe he balances the universe ethically as well. So if he's going to forgive the sin of some of his creatures, then to balance that, somebody's got to take the punishment for that. So the substitutionary atonement and some of those things actually makes sense given the fine-tuning that we see in the physical features of the universe. Maybe ethically the universe is fine-tuned as well. And thus, Jesus really did have to pay for all the sin to keep the ethics in the universe balanced overall. There's a standard of justice there that I can see an image of in the balance in the universe. It's like, oh, that was a huge thing for him to have to take. Yeah, wow. So, why? I mean, I don't care for ants, right? You know, if they've ever gotten in your kitchen, you wouldn't care for them either. You know, so why in the world would God decide to forgive those things that rebelled against him? And then to have to suffer the consequences to balance out the moral equation in the universe to do that. Because if you've spent years crafting something as a master craftsman, you could fall in love with that. And thus to give yourself for them can make some sense as well, but nevertheless, it still is an incredible thing. Especially to me in thinking about it, and this was a huge point I found as a Christian, becoming a Christian, was it's not just, the whole human race, but it's for us individually and personally that God has that attention. But if he can shape the universe to 1 part in 10 to the 55th here and 1 part in 100,000 here, you know, it's cool for him to have a personal care and a personal attention for us as well. And thus, to me, the ultimate fine-tuning, if you will, is that it shows us there's a creator of the universe who really can be our friend if we're willing to come to him. It's incredible. So with that, I will close. Thank you.